Okay, thank you very much. And so let me briefly recapitulate what we have seen and what I'm going to show you in this last lecture. So we are studying the minimum of this functional I epsilon of u, which is defined as the integral of epsilon over 2 u dot square plus phi of u with respect to the weighted measure mu epsilon with u in AC to log, u of 0, u bar given in the domain, just a fixed idea of phi. And we also define the value function which is exactly the infimum of, and under the compactness assumption I started with, is really a minimum of this integral functional among all the u in AC to log with given initial data. And we have seen that this value function satisfies the dynamic programming principle. So the epsilon of u bar is always the minimum of the integral from 0 to capital T of epsilon over 2 u dot square plus phi of u in the mu epsilon plus e to minus capital T over epsilon, the value of the value function in the final point of the trajectory. Okay. And we have seen that it satisfies this sort of approximated gradient flow equation. So if I evaluate the time derivative of the value function along the minimizer, so let me call it now u epsilon, the minimizer of I epsilon of u, then at some time t, this is exactly, so minus the derivative, is exactly 1/2 u epsilon dot square plus this quantity that I call now g epsilon of u square, and this quantity is a sort of approximated slope, is just the phi minus v epsilon divided by epsilon, calculating the point u. Okay. And what I mentioned yesterday is that we want to pass to the limit in the integrated form of this equation. I justified yesterday that this is a reasonable replacement of the slope, let me call in this way, the slope of the value function itself. And so if you are putting this quantity here, you are really following the gradient. U epsilon is really the gradient flow of the value function. This has to be understood in a suitable, is not the real pointwise slope, but is still sufficiently strong to control the derivative of the value function along any absolutely continuous curve for which phi of u is integrable. And eventually what we want to prove now is that we can pass to the limit in the integrated version of this identity, which I write in this form, the epsilon of u epsilon of t plus 1/2 the integral from 0 to t of u u epsilon square plus g epsilon square of u epsilon integrated from 0 to t is equal to v epsilon of u bar. Okay? And now the question is how to pass to the limit as epsilon goes to 0. Okay, so we have to check a few steps. First of all, we need to prove some reasonable compactness, and we want to show that the sequence u epsilon for arbitrary final time, you have these a priori estimates uniformly with respect to epsilon, and the integral of phi of u epsilon ut is less than c. By the compactness theorem I showed you in the second lecture, from these a priori bounds, we can conclude that there exists, so one implies that there exists a subsequence u epsilon n such that u epsilon n converge to u pointwise. And moreover, the metric derivative weakly converge to some, say, v in the limit in L2 lock with the v greater than the metric derivative of the limit. So the limit is in AC2 lock and is a right candidate to be a solution of the limit equation. So first, compactness. The second point that we have to show is that since we have just a subsequence converging pointwise, we have to understand what is the possible limit of this v epsilon along an arbitrary convergent subsequence. So the second ingredient will be a sort of gamma limit of v epsilon. So we will show that the gamma limit as epsilon goes to 0 of the functional v epsilon is exactly phi. So this means in particular two things, that if you have a sequence of points xn converging to x, a sequence of parameters epsilon n decreasing to 0, and you consider the liminf of v epsilon n on xn as n goes to 0, this liminf is always bigger than phi of x. And second information, which I write is important like this one, is that you have also a pointwise limit. So if you keep fixed x, you have that the limit, and not only the liminf, as epsilon goes to 0 of v epsilon of x, this is always equal to phi of x. Remember that v epsilon is always bounded from above by phi, so if you have this liminf, you have also this pointwise limit for free. Okay, so by these two properties, we are able to pass to the limit here by taking just the liminf. In this, applying 1, we know that you are fixing t for t fixed along convergent subsequent. We have that here, taking the liminf, we surely control phi of u of t, u is the limit obtained in this step 1. Of course, taking the gamma limit, the limit, you will pay an inequality here. By using the pointwise exact limit, since we keep the initial datum fixed, here you get exactly phi of u bar. By using this estimate, you may assume that the metric derivative is weakly converging in L2 lock. So this will be by the weak lower semi-continuity of the L2 norm. You get in the gamma limit here, in the limit here, the integral of v square. V square is an upper bound of the metric derivative. So here is easy to check that you get the metric derivative of the limit. This is still the second part of step 1. And eventually, what you want to have here is the worst situation. Since you have no controls on this quantity, you will define and study, in some sense, this will be the third step, what is the gamma limit of this slope. And I will call this how it is defined, as epsilon goes to 0, is the infimum of all the possible lim inf as n goes to 0 of g epsilon n on xn among all the possible sequences converging to x. Okay, this is the gamma lim inf of your functional. I will call it g minus of x, and the best that we can show here is that you have g minus of u of t square, another 1 alpha is already in front of the integral in the R. Okay? So this is the standard technique. And this is exactly what you get also by the minimizing movement approach. The only difference is that you don't take the gamma lim inf of this strange slope, g epsilon, but you take the gamma lim inf of the real descending slope. What is interesting concerning step 3 is that you may, I will write here, you have this two interesting estimates, 3 in fact. The first estimate tells you that, tells you an interesting information about the pointwise limit. So I will also denote by g of x the lim sup as epsilon goes to 0 of g epsilon of x. So this is the pointwise limit, and we will show that the pointwise limit is always bounded from above by the descending slope of the functional. So from one side, this, so if you are bounding from above the pointwise limit, of course, you are also given an upper bound for the gamma limit. So in some sense, the descending slope is always bigger than this object. And we will also show that the relaxed slope, this gamma lim inf, will always bigger than the relaxed slope. And this is defined as the gamma lim inf, or the relaxation, so it's better the relaxation of the descending slope. So what you have at the end is that you have a very big object in some sense. The best object is the descending slope. It controls pointwise this limit. This limit controls this relaxed object, but this relaxed object is always bigger than the relaxed slope. So at the end, these two objects coincide. So there is no difference to obtaining the limit, the relaxed slope, or this quantity. In particular, if you are in a situation, a good situation, where the slope is lower semi-continuous, then this object is exactly coincide with the slope. I will discuss this at the end of the lecture. But just to give you, say you in advance that this strange quantity is not so bad as it seems. So is more or less the same that the object you obtain by taking all the possible limit starting from the slope. And I will also show you that this quantity is also interesting since it provides nice pointwise estimates. Okay, this is the plan of the lecture. And now I will start from the step 1. Yeah. Yeah. Yeah, exactly. You may think this way. The recovery sequence is the constant sequence. Yeah, yeah. So if you keep the point fixed, you always converge to phi. Since this, in some sense, is a consequence of the fact that the limit of this object is bigger than phi, but all these quantities are bounded by phi, since we always have that V epsilon is less than phi. We have seen this in the previous lecture. So all the possible limits are bigger, but since you have also the lim sup is bounded by phi, you have the identity. Okay, any other questions? Okay. And now let me start with the first step. Before, let's say that the first estimate is already provided by this integrated version. So since the argument is easy, you have that the integral from 0 to an arbitrary capital T of 1/2 u dot square with respect to time, you throw away the gradient square, and is bounded by a constant, which is V epsilon of u bar, and this is not a constant, but this is always bounded by phi of u bar, minus V epsilon of u epsilon t. And in this situation, we have seen that V epsilon is a functional which is bounded from below as a lower quadratic growth. So this quantity is bounded from below locally. And so from this, you get that all this part is bounded by a constant. You need some extra work here to remember that we have proved that the epsilon of x is always bounded by minus a constant a minus 2b, the distance square of x from a reference point in your space. This was one of the first a priori bound I gave in the second lecture by using the Poincaré inequality. And then plugging in this quantity and using Gromval, you may prove this a priori estimate. Or if you prefer, just to simplify, think initially to the case where phi is non-negative, then V epsilon is non-negative, and then this is trivial. So this is Gromval. So apply Gromval in general, trivial if phi and thus V epsilon is non-negative. And now we want to recover an estimate also for phi, since we want to apply the compactness theorem, and we need an integral estimate on phi, since are the sublevels of phi that provide us enough compactness for your sequence. And the point is that we want now really identify. Remember, yesterday I mentioned that in the inner variation equation, that is phi minus phi of u epsilon minus epsilon over 2 u epsilon dot square, we have this equation, the distributional derivative of this object plus u dot square is equal to 0. And you guess, comparing this equation with the equation for v epsilon, that v epsilon of u epsilon is the absolutely continuous representative of phi minus epsilon over 2 u epsilon dot square. So remember that this is just a Sobolev function. What I'm claiming here is that his continuous representative is given just by the value function along the curve u epsilon. This is an absolutely continuous function. This is, since we have seen yesterday that along any curve with absolutely continuous, with the integrable phi, this functional is absolutely continuous, and then we identify it with phi. This is not difficult, but what we gain by this identification, we gain the fact that this functional v epsilon is bounded. So you get, in particular, that phi of u epsilon is equal to a bounded function plus an integrable function. Okay. This is bounded, this is integrable. So you see that you have this is uniformly integrable by this estimate, and so you see that also by this quantity you have the integral from 0 to capital T of phi of u epsilon of t, and dt is bounded by another constant c. Okay? And how we can identify these two functional? Start before the identification, let me call w epsilon the AC representative of phi of u epsilon minus epsilon over 2 u epsilon dot square. So we know that there exists at least one, there exists a unique continuous representative, and then we use this by evaluating the integral from A to B, an arbitrary integral of the integrand of the I epsilon u. So let me use this W epsilon to evaluate this integral from arbitrary points A and B. Then observe that you can rewrite the integral in this way. You add 1/2 to u dot square, so you get u epsilon square here, and then you subtract it, so you write phi minus epsilon over 2 u dot square in the mu epsilon. And now here you may recognize exactly the derivative of this functional. Sorry, not here. This is exactly this functional, not the derivative. But on the other end, we know that u dot square is equal to minus the derivative of the epsilon, w epsilon. So here you get, you can write this integrand in this way, minus epsilon, the derivative of w epsilon of u epsilon, plus of epsilon r, plus w epsilon r in the mu epsilon. Okay? Now you integrate by parts, and you get exactly the value w epsilon at a, e to the minus a divided by epsilon, minus w epsilon at b, e minus b divided by epsilon. Okay? Now you pass to the limit, you choose a equals 0, and you get that for a equals 0, this quantity is exactly w epsilon of 0, and pass to the limit when b goes to plus infinity. If you pass to the limit when b goes to plus infinity, observe that this functional w epsilon is not increasing, and has when you multiply by e to minus t over epsilon has finite integral. So you may easily prove that this quantity goes to 0. So passing to the limit as b goes to infinity, you get that the integral from 0 to plus infinity of the integrand, so epsilon over 2 u dot square plus phi of u epsilon in the mu epsilon is exactly the w epsilon at 0. But this is the definition of the value function, so they coincide. So just use this property to integrate by parts and see that the term in b goes to 0, and you identify with the value function. Okay? So combining these two results, we have checked the step 1. And now we have to look for 2, so to get the gamma limit of the value functional. I would say that after 4 lectures, I start liking this system to erase the blackboard. Okay. Maybe we can also import it in, but we don't have this stuff in the lecture room. Okay, so let me show you the second point. So what is the idea? This is not difficult, since you start with a sequence of points, xn, which are converging to x. In order to prove this gamma limit, I will just check this inequality. So I start with this sequence of points xn converging to x. I fix epsilon n going to 0, and then I express my value function in xn. I may extract a subsequence such that this quantity converges exactly to the Lim-inf, and I express this value function by using exactly the minimizer, so epsilon n over 2 un dot square plus phi of un in the mu epsilon n. So I may assume that this quantity converge up to extraction to the Lim-inf v epsilon n xn, and I may also assume that this lim-inf is finite, otherwise the inequality is always true. So in practice, this quantity on the left-hand side are bounded. So by the compactness argument I've shown before, I may extract a further subsequence such that un is converging. So I also assume that un is pointwise converging to some limit u, pointwise. And what is crucial is that I may also assume that the integral of u dot square in dt is bounded by a constant c, which depends on capital T, of course, okay, of un. This provides you a uniform estimate that tells you that the distance between un, this is crucial, of t from from the initial value xn is bounded by this constant multiplied by the square root of t. This follows by the uniform Hölder property, 1/2 Hölder regularity of un. Okay? Now the basic idea is to rescale this integrand, and rescale means that we put s t over epsilon, so t is epsilon n s. So we have this integral can be rewritten as 1 over 2 epsilon n u dot n square evaluated in epsilon n s plus phi of un evaluated in epsilon n s, and everything here is integrated with respect to e minus s in ds, just by changing variable. Now assume for a moment that phi is non-negative. Then you throw away just this positive quantity, and so this can be done always, but you can conclude this phi is non-negative. This quantity is always bounded by the integral from 0 to plus infinity of phi of un epsilon n s e minus s ds. And now you just use phi2, since observe that un applied in epsilon and s for every fixed s, thanks to this uniform quantity, un of epsilon and s is converging to x, the limit. Since the distance from this quantity to xn, you may use the triangle inequality, the distance of this point to x is bounded by the distance of un epsilon ns from xn plus the distance from xn from x. This is converging to 0, and this is uniformly estimated by Hölder. So this means that all these points are converging to x using phi2, since phi is lower semi-continuous, if it is non-negative, this will be bigger than the integral from 0 to plus infinity of phi of x e minus s ds. Since this measure is a probability measure, you get phi of x, which is, of course, in the limit. And goes to infinity by phi2. Okay? And what happens is phi is non-negative. You have to play with the trick I used in the second lecture, subtracting and adding a suitable non-negative quantity, which was this quantity ln of t, was the integral from 0 to t of un dot in the R, and then you subtract the square of this quantity, you add the square of this quantity in order to get here by Poincaré a non-negative quantity, here a non-negative quantity, and you apply the same trick. So then non-positivity is not a problem. But just to see the idea, in practice, the gamma lim-inf is easy since in v epsilon you throw away the contribution given by the metric velocity, and what remains provides you exactly phi of x. Okay, and so I've also checked the point 2, and now I want to spend some words about the behavior of G epsilon. No, we have to use that. So in order to study this behavior, it is still useful to introduce another quantity to express the value, the functional I epsilon in a different way. And this is step 3, the study of this strange quantity. And in order to, let me rewrite here the definition of the integral functional. Okay. In order to write in a different way this functional, it's useful to introduce the energy of the curve, which is associated to this path u. The energy is just the integral from 0 to t of the metric velocity square. Okay. The L function I used before was just the integral, the length. Here we are integrating the square. And I'm introducing this quantity since, of course, the derivative of this function is just the metric velocity itself at every point t, almost every point t. And so you may rewrite this integral by observing that this is the integral of epsilon over 2 u dot square in the mu epsilon is equal to the integral of epsilon over 2, the derivative of this functional. And then you may integrate by parts, and this gives you the integral from 0 to plus infinity of 1/2 e of t in the mu epsilon by the property of the functional. So in practice, you have here the integral from 0 to plus infinity of 1/2 the energy associated to the curve u plus phi of u of t in the mu epsilon t. Okay? And the epsilon disappears. Okay, now I want to show you the upper bound of this pointwise limit gx in terms of the slope. And in order to show the upper bound, since this g is defined, I rewrite here, g of x is the lim sup of phi minus v epsilon divided by epsilon, as epsilon goes to 0 in x. If I want an upper bound of g, I need a lower bound on e epsilon, and so also on v epsilon. In order to get such a lower bound, I use here the optimal curve. If I put the optimal curve inside, and then I can replace I epsilon with v epsilon of x. And then I observe that Et, the energy, by the Hölder inequality, this is always bigger than t multiplied by the mean value from 0 to t of u dot square. Then you use Jensen, and you get that this is bounded by, from below, by t, the mean value of u dot square, and this, the mean value of u dot is always bigger than the distance. So you have here the distance square between the initial point and the ut, u0, say, divided by t. Okay? So I look for a lower bound, so for every time t, I may substitute this energy by this quantity. So you say that this value function is always bounded from below by the integral of 1 over 2t, the distance square of the initial value, which is x from ut, the optimal map is a u epsilon in some sense, plus phi of u epsilon of t in the mu epsilon. Okay? Now you recognize here an expression which is quite similar to the one defined the Yoshida approximation of phi. Remember that the Yoshida approximation at x is just the infimum of the distance square of x from y divided by t plus phi of y, the infimum with respect to y. And so inside the integral you have exactly a candidate bounding from above the Yoshida approximation. So inside the integral you can substitute the Yoshida approximation, yt. So you have yt of x in the mu epsilon. So this is a nice formula that I rewrite it since it deserves to be noticed, which relates the value function to the Yoshida. So the value functional at a point x is always bigger than the integral with respect to time of all the Yoshida functions. This is a nice formula. I mentioned in the second lecture that these two functions are strictly related. And now, by using this fact, you may easily bound the g of x. Why? Since now phi minus v of epsilon of x is less or equal, you put phi of x inside the integral, since mu epsilon is a probability measure, and you get phi of x minus y of t of x in the mu epsilon of t. Now you want to divide by epsilon, and you divide by epsilon, but and then you rescale variables. By rescaling variables with the same trick as before, you put t equal epsilon s, and so what we get here, we get this inequality, the integral from 0 to plus infinity of phi of x minus y t epsilon of x divided by epsilon multiplied by e, sorry, there is an s here, e minus s ds. So you divide by s, multiply by s, and this is an identity, in fact. Okay? Now you can pass to the limit. You can pass to the limit by recalling that the lim sup of phi of x minus y of eta of x divided by eta, as eta goes to 0, is exactly 1/2 the slope of phi square at x. So this is a characterization of the descending slope in terms of the Yoshida approximation. And so you use the reversed Fatou lemma here. You pass to the limit as epsilon goes to 0, and then you get that the lim sup, when epsilon goes to 0, of phi minus v epsilon divided by epsilon of x is less or equal the integral from 0 to plus infinity of the slope of phi square at x, 1/2, which comes from the lim sup of this quantity, multiplied by s e minus s ds, and this is still a probability measure, and you get 1/2 d phi square of x. This is the estimate. So in some sense, this trick shows you that this difference, look to this quantity, this difference always is controlled by the worst situation when you take the minimal possible point here in the Yoshida approximation and provides you the pointwise estimate. So I'm running out of time, and I want just to conclude by recalling the other what you can say in the opposite direction. So this shows you that g of x, the pointwise limit, is bounded by the slope, and I want just to recall two other useful results in the other situation. And the other result is this useful estimate. It tells you the following thing. Take a point x and take an arbitrary curve. The idea is that you have a point x here, and take an arbitrary curve w of w, passing at some point t0 is equal to x, and assume that w is as usual AC to loc of some interval with values in x, and phi composed w is in L1 loc. X is an interior point, okay? Now compute the phi minus v epsilon divided by epsilon, evaluated exactly at x. And the crucial property is the following. Assume two things. Assume that, no, you have a general, you don't really need to assume any other thing. This quantity, the lim inf, as the lim sup as epsilon goes to 0. This lim sup is exactly this pointwise slope, always bound from above. What? The lim inf of phi of w, of phi of x, which is phi of w of t0, minus phi of w of t0 plus h, divided by h, as h goes to 0, minus the lim sup, as h goes to 0, of the energy, which is, let's say, the integral from t0 to t0 plus h of W dot square in the R divided by H. There is 1/2 here. And assume for a moment that T0 is a differentiability point of phi. Then what you get here, this comes exactly from the variational structure of your V epsilon. And assume for a moment that X is a point where phi along this curve is differentiable. Then you get here phi prime of W of T0. And assume also that this is a point where the metric derivative exists. So this is just 1/2 the metric derivative of W square, exactly in T0. Okay? So this quantity, which we call the 1/2 G of X square, bounds this difference of these two functions. And what is interesting is that here you may also play with the velocity of the curve. So replacing W with all its possible rescaling in time by a constant, you may play with a further constant delta here and another constant delta square here for arbitrary delta bigger than 0. And so you have delta here, delta square here, so that you may optimize with respect to delta. Assuming that this quantity is positive and optimizing with respect to delta, so choosing delta equal phi prime of W of T0 divided by dot the matrix velocity at T0 square, you get here that 1/2 G square of X is always bounded by the derivative of W at T0 square divided by 1/2 the metric velocity of W at T0 square. Okay, if you put this quantity on the right-hand side, you get exactly what you want, since you get that the derivative of phi along the curve is bounded by this pointwise slope G of X multiplied by the metric velocity of the curve at T0. So it tells you that G of X is really a good candidate to be a slope, at least along curves. So it is bounded from above by the global descending slope, and it bounds from below any derivative of phi along the curve. So it's a good candidate to be an upper gradient. So just to conclude, the further step is to prove exactly that using this inequality, the relaxation of G, what you have inside this integral, bounds from above the relaxation of the slope. So just misstate the final possible conclusion of these estimates. Just to see result, assume that the relaxation, the relaxed slope, defined as the gamma Lim inf of the standard slope, is an upper gradient. phi. Then g minus of x coincided with d minus of phi is also an upper gradient. For phi. And the limit function u obtained by passing to the limit satisfies the standard property of gradient flow, so phi of u of t plus 1/2 the integral from 0 to t of u dot square plus g square of u of t in dt equals, since you have a right upper gradient, phi of u bar, and equivalently the time derivative of phi along u is equal to minus u dot square equal minus g square of u of t, and by this identity this is also equal to minus the relaxed slope phi square along u of t. In particular, this property holds if phi is lambda geodesically convex in X. So for lambda geodesically convex functional, then you have that the relaxed slope is always the relaxed slope of phi is always coincides with the slope of phi, which is lower semi-continuous, and so it coincides with the pointwise limit g of x, and it coincides with the relaxation g minus of x. So all these notions coincide in the case of lambda geodesically convex function. For arbitrary functional, the idea is that whenever you have a lower semi-continuous upper gradient, what you obtain here coincides with this lower semi-continuous upper gradient, and still you have a gradient flow. Otherwise, you have, if you don't have a lower semi-continuous upper gradient, then you have to better investigate the property of this object, which could be a difficult task, as Daniel knows. Okay, I thank you very much for your attention and patience for attending these lectures, and thank you again. It gives us?
You give something up, because you are your value function mostly defined only with some of the local velocity, whereas in the for your Yoshida approximation, it's a global metric.
Yeah.
Is there a way to avoid this step, so that you do not really use the metric, but still pass to the limit? I mean, the situation that it's a clear interest thing, that you do not have a global metric, but only have.
Yeah. Yeah. So in some sense, of course, this method maybe is more complicated than the minimizing movement one. One of his advantages is that in many situations, in particular in infinite dimension, is easier to control the derivative of phi along curves. In particular, consider the lambda geodesically convex functions. Then the standard trick is to control the derivative of phi along geodesics. So they are definite curves, and along curves, absolutely continuous curves, the right object is this function g of x. since it perfectly controls, I raised it now, but the directional derivative along curves. You may think that he is in some sense the biggest directional derivative of phi along absolutely continuous curves. The slope is defined more globally, and when you evaluate the slope, you have to check the distance. You check the difference quotient by phi of u and another point, and you don't really need that there exists an absolutely continuous path connecting two comparing points. In some sense, g of x forces you to restrict the competitors among points which are connected by continuous paths. This is my idea. And at the end, since you want to construct a gradient flow, you hope that starting from your initial datum, you have an absolutely continuous path. So it's not useful to check all the possible descending directions, since at the end you want to control just the direction along a path. In this sense, I think that g of x is better, but in the opposite way, we know now that his relaxation is still bigger than the relaxation of the slope, and so at the end, all these notions in the limit will coincide. The crucial point is to get this lower semi-continuity.